Hello, I'm Joshua Friedman, Senior Analyst at Rapaport, and welcome to the latest episode of Rapaport's LinkedIn Live series, Gem Talks, in which we speak with experts from the diamond industry about important topics affecting the sector. This episode of the Gem Talks LinkedIn Live is brought to you by GIA, the Geological Institute of America, protecting consumers and supporting the global gem and jewelry trade since 1931 through research, education, and laboratory services. Today's topic is super deep diamonds. The way we categorize, sell, and price diamonds is mostly tied to visible physical characteristics. Other factors such as provenance have become more important, but still it's primarily the 4Cs that determine the desirability. However, what if there were another factor, namely the origin of the diamond within the earth? This is where our special guest comes in. Dr. Evan Smith, Senior Research Scientist at the GIA in New York, is a published expert on large and high-quality diamonds that formed more than 300 kilometers beneath the Earth's surface. Known also as CLIPPIR diamonds, and Dr. Smith will explain to us exactly what that stands for. They're formed beneath the lithosphere and tend to have high color and clarity like the Cullinan diamond and the Lesotho Promise. Knowledge of these super deep diamonds gives an extra dimension when discussing these special stones, but also helps create a new narrative about diamonds in general and can be a window into the processes going on deep inside the Earth's mantle. At the end of this session, we will take questions, so please post your questions in the comments. But first, Dr. Smith will begin with a presentation. So welcome, Dr. Smith. It's great to have you here.
Thank you so much for having me. I'm very happy to be here. Thank you for that introduction. We're going to be talking about super deep diamonds. You may have heard this term super deep or sublithospheric, and it doesn't just have to be about the science. Before we get into that, I want to try to frame this in terms of diamond jewelry and how this might be something that you could really think about from a consumer's perspective. And we'll start with a simple question. Okay, what is a diamond? Now, if you answered diamond is a solid crystal of carbon with cubic symmetry, sp3 hybridization, and covalent bonding, you get full marks. But the answer I was looking for is a diamond is forever. Okay, and a diamond has all this symbolism that we attribute it with. It's got this idea of luxury and strength and, above all, enduring love. These are the ideas that we associate with diamond. And this ad campaign, A Diamond is Forever, was launched in 1948. And if you bring yourself back to 1948, well, a diamond, what was it? It was this rare natural crystal, something really special because it was this amazing, beautiful thing we find in nature. And it had these unmatched physical properties that actually make it ideally suited for use as a gemstone. And these two things, the rarity and the material properties, are really what forms the basis of why it's special. And this is the continuing idea, I think, that people have of what a diamond is. At the time in 1948, almost nothing, very little was known about how diamonds form, so it never really entered into the discussion. And I would argue that, currently, the story of diamond formation just hasn't really been part of its meaning and significance. And I think it's easier to appreciate this if we contrast it with some other material like this. There's this growing popularity of using meteorites, iron nickel meteorites, to fashion rings like this wedding band. And this is the complete opposite, where the material properties of this don't really matter so much. It's the formation story, the idea that this is from space. That's what gives it meaning and significance. And I think there's some room here to transfer this kind of thinking, this kind of sentiment over to diamonds, where its formation story could give it another dimension of meaning and significance. So let's talk about how diamonds form. We think about them in the family of gemstones. They're the king of gemstones, but in terms of their geology, they're quite different from almost all other gem materials. So here's a cross section into the earth. It's going down 200 kilometers here. So most gemstones like opals and sapphires and rubies, emeralds, they form somewhere in the crust of the earth. Okay, fairly shallow depths, maybe as deep as 20 or 30 kilometers. Diamonds are much, much different. So most diamonds form way deeper down in the earth at a range of 150 to 200 kilometers. So that's most diamonds, but we're talking about super deep diamonds. Some diamonds form even deeper than that. So deep we have to zoom out from this cross section, draw it a little bit deeper. So super deep diamonds are ones that come from around 300 to 800 kilometers deep. And this constitutes something like 1 or 2% of mined diamonds. That's kind of a rough estimate. And they come from this great depth and they ascend up closer to surface in low density rocks, okay? And they wait here at the base of the lithosphere with other diamonds, and they're brought up to surface in kimberlites. And these diamonds are a really active area of scientific research because we don't really have any other materials available to us at Earth's surface that come from such great depths. So they're a great opportunity for scientists to kind of get a sense of what happens deep in the earth, not just for diamond formation, but for the earth's activity in general. So how do we know anything about these depths? A lot of the information comes from inclusions that are trapped inside diamonds during growth. So here's a nice round brilliant diamond with an orange garnet crystal inside it. This isn't a super deep diamond, but it's a beautiful crystal, just an example. So inclusions trapped in diamonds are really well preserved. They're encased in diamond. It's a strong material and it prevents anything from leaving or entering. That little inclusion trapped inside, it becomes like a really well sealed environment and it's really well preserved. So this is a great thing to study if we want to understand what it was like when this diamond formed, or where it formed, or when it formed. These inclusions reflect diamond crystallization, and they also reflect the place, the environment, the mantle host rocks where this diamond grew. And the inclusions we see in diamonds, they change with depth as the pressure and temperature increase as you start looking deeper and deeper into the earth. So it's really the inclusions that tell this story. Here's an image I snapped of a really beautiful peacock colorful inclusion called ferropericlase. And ferropericlase was among the first things that we recognized as being maybe super deep in origin. So ferropericlase and another inclusion called majoritic garnet. It's a special kind of garnet that has excess silica beyond what we would normally expect for a garnet. People started to find these in diamonds through the 1980s or so, and they were compared with high pressure experiments. So these experiments where you take a rock and squeeze it to tremendous pressures and increase the temperature, you can see what kinds of minerals we start to appear as the pressure and temperature increase. Those experiments serve as the basis for comparison. And that's the reason why we were able to see some ferropericlase and majoritic garnet and make this connection to experiments and say, well, actually, some diamonds must have formed at extreme depths beyond this, 200-kilometer realm that we're used to thinking about for most diamonds. We began to recognize some diamonds were super deep, but the story really took off with the discovery of diamonds from the Joina area in Brazil. When De Beers was doing exploration work here, through the early and mid-1990s, there was an explosion of scientific study of diamonds from this area because many of them, a very high proportion, actually have inclusions of ferropericlase, majoritic garnet, and even other phases that we understand to have formed at great depths in the earth. So we learned a lot about super deep diamonds, and the field really exploded in the mid-90s through the study of diamonds from Joina, Brazil. And in understanding this extreme depth of formation, we had to back off in terms of diamond geology and our understanding of it and say, well, actually, there are at least, a couple different ways, very different ways that the Earth forms diamonds. It doesn't just form diamonds in one way. So in general, diamonds crystallize from carbon-containing fluids. It might be a melt or a kind of watery fluid percolating through the mantle, and there's some kind of reaction that causes that carbon to precipitate or crystallize out of the fluid or melt. And because of the high pressure deep in the mantle, that carbon crystallizes as diamond. That's the stable, solid form of carbon deep in the earth. And there are two major divisions of diamonds. So there are lithospheric diamonds formed around 150 to 200 kilometers deep. And we think of them as forming in the oldest and thickest parts of continents, something we call the mantle keel here. This is where lithospheric diamonds, most of the diamonds we mine, originate in this environment. And then with the study of Juina diamonds and other localities around the world, we started to recognize that there are diamonds that are super deep in origin. And these come from below the continents, below the lithosphere, down where the mantle is slowly moving through time. This is what we call super deep diamonds. And in all these different kinds of diamonds, there seems to be this through-going connection always pointing back to this phenomenon called subduction. Subduction of oceanic lithosphere. And that's drawn in this diagram here as this bent plate. So this is the oceanic floor, the tectonic plate that makes up the ocean floor. And sometimes these plates will bend and sink into the earth. And they dive down, right down through the mantle transition zone into the lower mantle. And it seems as though these subducted oceanic plates are an important part of driving diamond growth. They can provide carbon and water to help flux the growth of diamonds. So we're going to be taking a look deeper down in the earth here, and keep in mind this concept of subduction. So I mentioned ferropericlase and majoritic garnet and alluded to some experimental work. These diagrams here show the main findings of some of that experimental work, taking a rock like peridotite or basalt. These are the two major diamond host rocks we think of where diamonds grow. And we'll just concentrate on the middle diagram first here. So if we think about peridotite, this is the rock type that makes up most of the mantle. Close to Earth's surface, it's made up of a lot of olivine, that's one mineral, and garnet and clinopyroxene. But as you go deeper down in the Earth, okay, deeper past 400, 600 kilometers, even down to 800 kilometers, some of these minerals change. As the pressure and temperature increase with increasing depth, some minerals break down and new minerals form. So we can understand what we expect to happen based on experiments. And this is kind of the roadmap for what the mantle ought to look like. And on the right side, we've got a similar diagram. Instead of peridotite, this is basalt, like oceanic crust. That's the rock it's made up of. And as you subduct the ocean crust, bring it deeper down into the earth, the mantle mineralogy changes. And you go from something that's dominated by garnet and clinopyroxene to something that changes in its mineralogy. And when we get down to the lower mantle here, past this boundary of around 660 kilometers, we have a completely different set of minerals that make up the rocks there. And these are the kinds of minerals that we find in sublithospheric diamonds. Quite often we see things like, I mentioned ferropericlase shown in this brown field here, or majoritic garnet, which is something we expect to see, deeper than about 300 kilometers down in the earth. And it exists all the way down to the lower mantle, and then majoritic garnet disappears and other minerals form. So the experimental work that made these diagrams possible has been hugely important for understanding and reading what we see as inclusions inside diamonds. So on the previous slide, I was talking about subduction and plates moving around. And you might be familiar with this idea of plates moving around as plate tectonics, okay? And this is the popular, diagram, the popular sense of plate tectonics that most people know, where the Earth's surface is made up of these rigid plates that move around and they bump up against one another. This is what causes earthquakes, okay? But this is only part of the story. What we see is plates moving at the surface of the Earth becomes much more interesting if we consider it in cross section. What's happening in the vertical dimension, I think, is a lot more interesting. In the vertical dimension, we can appreciate that the Earth's surface is made up of two very different kinds of plates. Okay, you've got the plates that make up the continents, and then you've got the plates that are underneath the oceans. So oceanic plates, the lithosphere here is thinner and it's generally much younger. It's always in this process of being created at mid-ocean ridges, living some life of, hundreds or maybe even 200 million years, and it doesn't survive much longer than that before oceanic plates bend and subduct down into the mantle, almost like a conveyor belt. This is a continuous process that's been going on for billions of years, and it's really important for shaping the surface of the Earth and regulating the exchange of materials like carbon and water from Earth's surface to the Earth's interior. And you'll notice I've drawn a little question mark down here because there are a lot of things we don't know about, what happens to these plates, what do they carry with them, and how much do they carry with them? What gets actually returned down deep into the Earth? Part of the difficulty in understanding this leg of the process is that we can't drill down and see what subducting plates look like. We don't have any samples. We can't visit this place, so it's largely hidden from view. And, spoiler alert, diamonds actually give us a lot of insight into what happens deep into the Earth and can help with some of the unanswered questions as to what happens to subducted plates and what do they do for the Earth. So subduction is one word that just comes up again and again in diamond geology. And I think now the emerging picture is really that subduction fuels maybe not all diamond formation, but many diamonds seem to be connected to this concept of subduction. And, I alluded to this idea of things being brought into the Earth, like carbon and water. And a really nice example of that came out in 2014 when this diamond made headlines. This was a super deep diamond from this Juína region in Brazil. And it had an inclusion of something called ringwoodite. This is kind of a high pressure version of olivine. And it forms somewhere around 520 to 600 kilometers deep in the Earth's mantle. But what was special about this inclusion of ringwoodite was that it was hydrous. Okay, it contained a lot of water in it. It had like 1 or maybe even 2 weight percent water dissolved in it. This was a really important observation for showing that there really is water down deep in the Earth. And the most popular reasoning behind that is that this water has been carried down deep into the mantle transition zone by the process of subduction. So this is one of the strongest pieces of evidence we have for the existence of water down there and linking it to a process. Where does that water come from? This idea of drawing water from the Earth's surface down into the Earth matters a lot because just look at the Earth. I mean, Earth's surface is just loaded with water. And this is probably the most geologically important surface we have, the interface between the ocean and the oceanic plate, the ocean crust and the underlying mantle lithosphere of that oceanic plate. All around the Earth, there's this ongoing interaction between seawater and rocks, and eventually that oceanic plate will bend and subduct and dive down and sink into the Earth's interior. So if it carries water and carbon and other elements with it, that's a really important conveyor belt or process that we want to understand because it probably helps regulate the composition of the Earth's surface and Earth's interior through time. So going back to the diamonds, these diamonds, like the ones from Juína and from other parts of the world for years, this is what we thought super deep diamonds looked like. They're usually pretty small and not gem quality. But that all changed in 2016. I published a paper in Science that actually showed that these are also super. So it went from being something that was kind of obscure and not very interesting in terms of the gem aspect to being something that's front and center. So these diamonds are super deep diamonds. Some of these formed as deep as 660 or maybe even a little deeper, kilometers deep in the Earth's mantle. So the top of the lower mantle, very, very deep in the Earth. And if you're looking at these, you might recognize, well, these are type 2 diamonds. And yeah, you're right. Okay, diamond type is an important concept in diamond geology. It's one of the ways we classify diamonds. You've got type 1 diamonds. Okay, they contain nitrogen substituting for carbon in the diamond crystal structure. And type 2 diamonds, ones that don't have any detectable nitrogen in infrared spectroscopy. These type 2 diamonds are rarer and they're purer. And if they have just carbon, we call that type 2A. If they have a little bit of boron with them, we call that type 2B. And type 2B diamonds, that boron content can sometimes make them blue. A great example is the Hope diamond. So these diamonds that I'm showing here, we understand that they're super deep diamonds. You could also think of them as type 2A and type 2B diamonds. But from a geological context, not all type 2 diamonds really belong in this category. There's a bit more to them here. And that's the reason why I gave them this name, CLIPPIR, okay? So down here in the lower left, this is a good example of, the kinds of large, beautiful type 2A diamonds we see coming out of the Letseng mine in Lesotho. So it's not just that these diamonds have very little nitrogen in them. These diamonds are also generally large. They're generally very high clarity, so they're inclusion poor. They're generally very pure, so they're usually type 2A, but sometimes they have a little bit of nitrogen in them. So they're very pure, and their shapes are irregular, and the surfaces of them are often resorbed. So they've been rounded and kind of etched chemically by interaction with fluids or magmas. That's resorption. And I've tied them to the best example of a diamond like this, I think, is the Cullinan diamond, the largest gem quality diamond ever found at 3,106 carats. That diamond serves as kind of a type example for these diamonds that I've given this acronym CLIPPIR. So diamonds that are like the Cullinan diamond, we now refer to them as CLIPPIR diamonds, at least when we're talking about their geology. So these diamonds are CLIPPIR diamonds and type 2B diamonds. So there's the Cullinan diamond there on top of that royal scepter. So although these diamonds are usually very high clarity, especially after they've been cut and polished, they're not completely inclusion free. That's really important because remember, inclusions are one of the best ways we have of trying to understand how diamonds form. So here's an image of the Cullinan that I really like because it actually shows a couple inclusions through this cleavage face here. You can see into the crystal and see that it does actually have some inclusions in it, at least before it was cut and polished. You can say the same thing for the Lesotho Legend, this 910 carat diamond here. It's got these black spots in it, so it has something in it. And for many years, this stuff inside CLIPPIR diamonds was understood to be graphite. It certainly looks like graphite. It's black. It looks like flakes of graphite. Here's a window polished into the Lesotho Promise. And again, just to drive home this point about the high clarity, even when they have inclusions, when this diamond was cut and polished into all the various faceted pieces here, all of these pieces were flawless because those inclusions were polished away and removed. So they have very large regions of high clarity, even if you start with some inclusions here. So what actually are these? The thing is, even though they look like graphite, if you take a closer look under the microscope, sometimes you'll see that, inclusions like this, the largest part of it is this black flake, but they'll have this little teeny tiny crystal hiding inside it. That is the inclusion itself. That's the nucleus of the inclusion. And most of what we see, this large black flake around it, is actually a graphitic fracture. So there's been a fracture, like a crack that's opened up around this inclusion, and the diamond has converted from diamond crystal structure to graphite crystal structure, or maybe even amorphous carbon, and it's black. So even though most of what you see is graphite, I would say this isn't really a graphite inclusion. It's a mineral inclusion with a large graphitic fracture. And I spent a lot of time and effort screening through many, many diamonds coming through GIA to find inclusions like these in type 2A diamonds. and try to identify what they are using a technique called Raman spectroscopy. So if you can see the inclusion really well under the microscope, you can also analyze it using Raman spectroscopy. With this technique, you aim a laser at the inclusion and you record the light that scatters back off that inclusion. And that scattered light can contain information, a spectrum of what that material is. That's what I'm showing here. Here's a few examples of inclusions in CLIPPIR diamonds. And these are actually calcium silicates. The first two top inclusions here are calcium silicates, a mineral called bryite. And the bottom one here is something I mentioned previously, majoritic garnet. So right off the bat, we can see that we're looking at mineral inclusions that we don't normally see in most diamonds. These are mineral inclusions we see in sublithospheric diamonds. And this is the first clue that actually these diamonds formed at super deep depths, beyond 300 kilometers. So that immediately makes these diamonds a lot more interesting. And it's not just CLIPPIR diamonds. I showed type 2B diamonds as well, the ones with boron that can give them this blue color. This was one of the most exciting diamonds I ever examined. I just couldn't believe that this beautiful faceted crystal here had an inclusion in it. Under the microscope, I could see this, and I was so excited to identify it with Raman spectroscopy. And when it came back as a bryite inclusion, I was just floored to see that this too carries on this sense of super deep diamond formation. So the inclusions we see in both CLIPPIR diamonds and type 2B diamonds paint a picture of diamond formation in the mantle transition zone or lower mantle. So somewhere in an origin, maybe, I said as shallow as 360 kilometers or as deep as 750 kilometers. And there might be a range. It's not that we have total uncertainty. There might actually be a range over which these diamonds form, a range spanning a couple hundred kilometers deep in the mantle. And again, these experimental works form a roadmap to help us understand the mineral inclusions we see in these diamonds. So I would say that the inclusions we have in these kinds of diamonds, they resemble those reported previously in Geoina-like sublithospheric diamonds. And they're associated not just with these great depths, but also associated with deeply subducted oceanic plates. So echoing that process of subduction as being tremendously important for the formation of these diamonds. Now, this isn't all the inclusions we saw. There's one more category of inclusions that seem to be really important for CLIPPIR diamonds, and it's not on these diagrams here. The most common type of inclusion I found in CLIPPIR diamonds was something that looks like this, okay? It's a metallic inclusion, and metallic not just in its appearance, it's a metallic luster, obviously, but it's metallic in terms of its composition too. This inclusion here is a beautiful example of it. You've got this nucleus here that's actually made of a metallic alloy, and I can show you what this looks like in cross-section. I polished open one of these inclusions, and this is what it looks like inside. This is a false colored image where different elements have different colors. So iron is colored green, nickel is colored this pink color here, and sulfur is in this blue. So the mixture of sulfur and iron give us this kind of aqua color here. So these inclusions are actually a mixture of iron, nickel, carbon, and sulfur all together. And if you take this mixture back down deep into the earth, it would have actually been a molten mixture. So this was a melt when it was trapped. And we think that the best explanation here is that this actually served as the diamond forming medium. So you can imagine that this metallic liquid had carbon dissolved in it, and some kind of chemical trigger caused that carbon to crystallize out of that metal. And as that diamond was crystallizing, it trapped little tiny droplets of that growth medium. And those droplets are the inclusions we see today. Okay, so this was a totally unexpected observation. So all these diamonds now, we can say that they're forming at super deep depths, and we can say that altered oceanic lithosphere is a really important ingredient to their formation. We see diamonds forming probably as a result of this oceanic lithosphere subducting. And as it warms and deforms in the mantle transition zone and lower mantle as it reaches this boundary at 660 kilometers, there are a lot of things happening to this subducting plate that could give you fluids and melts that trigger diamond growth. And I'd like to highlight three here. First is the melting of carbonate. I've shown that with these red arrows here. So things like, imagine limestone, or calcite. These are calcium carbonates or magnesium carbonates. And as you go deeper and deeper into the earth, these things melt pretty readily. And this is one of the things that might melt out of this subducting plate and give you some kind of a melt or fluid that contains carbon and could flux the growth of diamonds. Another ingredient that's really important is water. So as this plate interacts with the ocean at Earth's surface, it might have the ability for colder plates to retain some of that water in minerals. So it's locked up in solid minerals that have water as part of their crystal structure. But those minerals don't survive forever. As you warm up this plate and take it to greater depths, those hydrous minerals can destabilize and break down and release that water. So suddenly you have the appearance of water, and that triggers melting in the neighboring rocks. So you can make this watery melt. And the third process, which is completely unexpected based on experiments or anything we were really thinking of, is this metallic melt, something that we have evidence of in these inclusions, but whose connection to subduction is still a little bit of a mystery. We know this metal comes from the Earth's surface. It arises through the interaction of ocean water and the sea floor through the process of serpentinization. We think that's where that iron is coming from, but exactly how it evolves during subduction is still a bit of an open question. And this is something that, I think might be tremendously important because it's something that we see in multiple places around the world expressed in these CLIPPIR diamonds and their inclusions. So I'm talking about diamonds forming deep down in the earth, but we're studying them and observing them and enjoying them at Earth's surface. So it begs the question, how do these get up to surface? And we made a really good discovery a few years ago by dating diamonds that showed that they must have moved in a certain way that seems to correspond to the movement of plates. And the theory that emerged from that is something like this. So diamonds form deep down in maybe the lower mantle or mantle transition zone, but they're forming within or within conjunction of rocks, host rocks that have low density and that might actually float, or they're buoyant. So these rocks could rise up to the base of the lithosphere, and you could have this diapir of kind of squishy, low-density rock with super deep diamonds in it that gets plastered to the base of 6 old continents. And it might sit here for millions and millions of years before eventually you have stage 2, where a kimberlite eruption entrains some of those diamonds along with lithospheric diamonds and carries them all up to Earth's surface. And a kimberlite eruption is what we see, or what we think would have happened at Earth's surface. We've never actually observed one erupt, but we see the fossilized remnants of these spectacular volcanoes that sometimes carry diamonds. So all of the diamonds are kind of mixed together and jumbled up and completely removed from their original geologic context. As we find them at Earth's surface, they're mixed up and they're entrained within this volcanic host rock. So there's a lot of detective work to piece together exactly where these diamonds came from, and also to recognize that there are multiple populations of diamonds that formed in different ways and maybe even at different times as well. So super deep diamonds have come a long ways. Now, in terms of gem diamonds, now we can kind of divide these two up into these categories where we've got most gem diamonds originating from the Earth lithosphere. These are very deep in terms of their origin, and some gem diamonds are actually super deep. They're sublithospheric in terms of their origin. That comprises CLIPPIR diamonds and type 2B diamonds. Now, coming back to the first couple of slides I showed you at the beginning, where we're talking about the ideas we associate with diamonds, I think this is very relevant right now in the industry, trying to struggle with, what is a diamond? Is it real? What's the difference between lab grown and natural diamonds? I think there's a lot to say here that emerges from the geological side of natural diamonds. And I think if we want to focus on what's kind of special about natural diamond, beyond just the idea that Mother Nature formed this crystal, I think there's a lot to say. Okay, so diamonds formed through these large scale movements of plate tectonics. They're ancient. Some of them are up to 3.5 billion years old. That's 3/4 of the Earth's age. These are the deepest derived things you can touch. Can you imagine wearing that on your hand or on your ears? And they reach surface in these really amazing, explosive volcanoes, kimberlites, and sometimes lamprolites. You really couldn't ask for a better origin story. And I think there's a lot of flexibility here and a lot of opportunity to introduce some of these ideas into the gem sphere and consumers' understanding and appreciation of what diamonds are. So, to summarize, inclusions are not just bad. Inclusions carry unique and valuable information that can be really beautiful sometimes. And through the study of inclusions, we've come to understand that there are diamonds that form below the lithosphere. These are called superdeep diamonds in the range of 300 to 800 kilometers. There are diamonds like we see commonly at Juína in Brazil and many other localities around the world. But now we also have come to understand there are CLIPPIR diamonds that are superdeep. This constitutes most type 2A gems. And type 2B diamonds, like the Hope diamond, the ones that contain boron and are sometimes blue. These diamonds are sublithospheric. They're super deep. So it makes up some of the biggest and best diamonds out there. Now, I think it's really telling here. Earth is not a static ball of rock, as it might appear to us in our day-to-day lives. It's moving. Its interior is always in motion. Its surface is always in motion by plate tectonics and subduction in ways that shape the continents and mountains and oceans through time. And these are the processes that ultimately sustain life as we know it. Diamonds are unexpected creations, a product of our dynamic planet. And they reflect the very processes that make Earth so special. So I hope that you can take some of these ideas and transfer them into your meaning and significance that you associate with gem diamonds. Thank you.
Thank you very much, Dr. Smith. I very much appreciate that that presentation you've given us. Very interesting. Just a reminder to all of you listening and watching to post any questions in the comments. And for those of you asking, yes, there will be a recording available after this. I want to ask a few questions of my own, just to begin with. You mentioned in the beginning that originally not a lot was known about how diamonds were formed, and therefore the industry wasn't really able to capitalize on the diamond story. Now that more is known, have you seen this coming up more? Have you seen people in the diamond industry telling the geological story of diamonds more?
Yeah, that's a great question. I think to some extent, yeah, like some of these ideas are slowly percolating over into the gem world. I mean, diamonds are beautiful, and they've never really needed more of a story. They stand out immediately as luxury items that are self-evident as, a symbol of beauty and enduring love. But I think simple ideas like, for instance, the age of diamonds, that's a really easy thing for people to grasp. And that is a good example of this geological information that has made its way over into a more popular understanding. The understanding that diamonds are millions or billions of years old. And, and most diamonds are older than dinosaurs. That's a simple idea that I think people can latch on to. And I think there's probably more room to capitalize on those kinds of ideas, give something to appreciate about natural diamonds.
Do you think that the fact that it's specifically the the flaws in diamonds that give us the information that you've shared with us. Do you think there's also a potential marketing angle there, that it's the value is in the flaws?
Yeah, in my opinion, absolutely. I mean, people love it when you see a beautiful image of an inclusion, maybe a vibrant orange or pink garnet in a diamond. You know, it's a beautiful crystal. It's hard to see in your hand, but if you have the ability to magnify it, there's a lot to appreciate there, just in being a beautiful world trapped inside your diamond. And to extend it beyond just a beautiful inclusion, to actually associate some meaning with that inclusion, I think really is something valuable that at least some consumers could appreciate.
Okay, well, thank you to Jeff Politis for a good question that I'm about to read out. Jeff asks, on the retail side, would it be safe to say that most diamonds of 5 carats and above DIF Type 2A are super deep diamonds?
That's, yeah, there's kind of a gradational boundary there where it becomes true. I'd say at 5 carats, if you've got a D color Type 2A diamond, you've probably got, more than a 90% chance that this is a super deep diamond. As you look at larger and larger size diamonds, it becomes more and more true. So I have seen some examples of beautiful Type 2A diamonds that have inclusions that show that they're actually lithospheric diamonds. So it is possible to have lithospheric diamonds that are D color that actually are Type 2A. So you can't make a perfect equation there for Type 2A and super deep, but it does become more and more true as you look at larger sizes. I'd say 5 carats and up. Yeah, most of those diamonds are going to be super deep if they're D color, flawless, Type 2A.
Is there any sort of diagnostic test that you could do, or would it have to just happen to be the subject of one of your studies for us to know for
A
sure?
diagnostic test to tell whether or not something is super deep?
Yes.
I think it comes back to looking at the inclusions. And if you've got no inclusions, then you've got to rely on the kind of extra information like the absence of nitrogen. So if it's Type 2A, that's a good sign. And you have to associate it with other diamonds that we've observed in the past that do have inclusions. One thing that becomes really easy, I think, is when we start talking about Type 2B diamonds. All the Type 2B diamonds, like blue diamonds, like the Hope diamond, all of those where we've seen inclusions appear to be super deep in origin. So as soon as you start talking about Type 2B diamonds, natural diamonds, then I would say it's safe to assume those are super deep in origin.
Okay, and follow-up question from Jeff. He's asked, first he says, great presentation, and thank you. When will the GIA mention super deep origin in grading reports?
I don't know that there is any plan to do that. While it would certainly be interesting information to provide to consumers, I think it would be very difficult to give that information in a very factual, quantitative way for all diamonds. It would be something that you could only really do factually with 100% certainty for some diamonds. And again, it would come back to this question of inclusions. So I'm not aware of any intention to try to introduce that into, GIA's standard reporting.
Understood. Thank you. Question from Freddie Taylor. Do we know where in the mantle red diamonds come from?
Yeah, red is a color that's sort of like extreme pink. Okay, so we associate red and pink together, and the color there comes from defect that we kind of term the 550 nanometer band defect. We don't understand its structure in detail, but we know that it comes about due to plastic deformation. So the diamond has actually been subjected to some kind of stresses deep in the mantle that have deformed it and caused this defect that turns them red or pink. And this is something that we probably don't have in abundance in super deep diamonds. It's something that was very common at the Argyle mine in Australia. And we think that this process of turning them pink is something that happens at shallower levels. And to my knowledge, the only red diamonds that we've really understood through studies of inclusions are diamonds that originate from the lithosphere, so shallower diamonds. That's not to say it's impossible to have a super deep red diamond, but we just haven't observed that yet.
Okay, fair enough. Thank you. There's a question from Sumil Shah that looks like it's interesting, but I don't fully understand it. So maybe Sumil, if you're able to maybe repost that question or clarify what it was you were asking, we can ask that one. Question from Jonathan Griffith. How do scientists date super deep diamonds and their inclusions, and why might they be younger than shallower diamonds?
Yeah, that's a great question. So we understand the ages of diamonds largely through radiometric dating of inclusions. So we're not dating the diamond itself, we're dating the inclusions. And we're using radioactive isotopes. So versions of certain elements that aren't stable, and they break down through time through a stable, through a predictable rate. So when you look at an inclusion in diamond, it can have this kind of built-in internal clock. Reading that clock, actually measuring the age through radiometric dating, is a pretty involved process. You have to essentially extract the inclusion. So you destroy the diamond in this process, and it's not always successful. And the best ages come from analyzing multiple inclusions. So it's a really involved procedure. And for that reason, we haven't dated a whole lot of sublithospheric diamonds. The few diamonds that we have dated reliably, they do show younger ages. So they're not billions and billions of years old. They are somewhat younger, but we still need to do a lot of work to understand the ages of sublithospheric diamonds. I think there's a lot of work left to be done to fully kind of make a fair comparison between lithospheric diamonds and sublithospheric or super deep diamonds and really understand how those ages line up. We know that lithospheric diamonds are as old as 3.5 billion years, but there are some lithospheric diamonds that form much younger, as young as 90 million years ago. So we understand lithospheric diamond formation as something that's kind of episodic through time and spans a great range of Earth's history. And super deep diamond formation might also be episodic, and it might span a slightly different range of Earth's history. We don't know. We need more information to really flesh out that timeline and understand those relationships better.
Right, and on that topic, do you think there's an opportunity for the industry to make more of the fact that there are diamonds of different ages? Not sure necessarily charge a premium for a 3 million year old diamond, not a 3 billion year old diamond, but is there maybe a marketing angle there?
I think there already is a marketing angle that's being used right now to portray diamonds as millions to billions of years old. There's some difficulty there in taking, a random diamond from a mine and saying this diamond is an age of X. We can't do that because any diamond deposit has a mixture of multiple populations. So it's not as though all the diamonds from, say, Diavik or Akkadi, where we find those 3.5 billion year old diamonds, it's not as though all the diamonds there are that age. So we can't just take a diamond, even if we know what mine it came from, we can't assign an age confidently, but we know that many diamonds are older than 1 billion years. So there's some kind of disconnect there. But I think just the idea that these diamonds are among the oldest things that we can touch, I think is something captivating that I think is interesting to most consumers.
Okay, great. You mentioned a range of depths under the surface of the one particular one. You said 660 kilometers. beneath the surface. So that was the starting range. How do you get to measurements that precise?
So those levels come from the changes in mineralogy we see expressed in the inclusions in diamonds. So I mentioned ferropericlase. There's something in the mantle we expect to find alongside ferropericlase. That's a mineral called bridgemanite. It's a magnesium silicate. So if you've got a diamond that contains ferropericlase and bridgemanite, those are lower mantle minerals. And right off the bat, we have to say, well, this must have formed, around 660 kilometers or deeper, because at shallower levels, we don't find those minerals together. It's not really possible that we know of to make those minerals in a stable assemblage together. So there are these punctuated marks, depth levels, where we expect big changes in the mineralogy, the minerals that make up the mantle. And when we cross over those thresholds and we see some minerals disappear and new minerals appear, those are really strong pieces of evidence that mark the depth. So 660 is a big mark of depth where the mineralogy of the peridotite that makes up most of the Earth, mantle, and oceanic crust that makes up the top portion of that subducting slab, big changes in mineralogy happen as you cross into the lower mantle at that 660 threshold. So 660 kilometers is a very important boundary when we're talking about sublithospheric diamonds.
Yeah, thank you for the explanation. Question from Evelyn O'Hagan. Could you talk about how graphite fractures form from inclusions?
Yeah, that's a great question. Like this inclusion shown down here, it's got this big black fracture around it. So if you imagine this diamond growing and it traps this little inclusion, and now you bring that diamond up to surface where the diamond used to have a whole bunch of confining pressure squeezing the diamond from all sides, and now you bring it to Earth's surface where there's nothing confining it. So the diamond is able to expand and relax, but the inclusion trapped inside it is not able to expand and relax. So it pushes on the surrounding walls of the diamond. So there's a lot of built up pressure inside that diamond, and that inclusion can sometimes cause the diamond to crack and rupture, and it relieves some of that pressure. And as it relieves that pressure, now you can imagine the pressure inside that inclusion has gone from maybe a few gigapascals, very high pressure, down to something much lower. And the walls of that crack now have a lot less pressure on them. And if there's fluid there, like a watery fluid or carbonate kind of fluid, that can help turn the diamond into graphite, because graphite has a much lower density. So the carbon that makes up the diamond can relax and expand and take up some of that new space that's been created inside that fracture that's just opened up. So it's sort of a process that has to do with the pressure buildup inside these inclusions. It doesn't happen with all inclusions, but it's very, very common for the inclusions in super deep diamonds to have this kind of black graphitic fracture.
Okay. We've got another question / suggestion from Lisa Benaquista. Would the GIA ever consider photographing these unique inclusions of the diamond, offering the photos to the client as part of the birth certificate of the diamond, something different from the plot on a report?
Yeah, I think there is a growing appetite for that kind of service. And I think it's something that GIA is uniquely suited to do. If diamonds are already coming through the laboratory, we're already examining them under the microscope, and it wouldn't be that difficult to snap a photo of some of these beautiful things we see inside the diamond. So it's not something we offer currently, but I think there's certainly an appetite for that. And it's something, I would love to see that if you could buy a diamond and also get some images of the beauty that is hard to appreciate with the naked eye that's inside that diamond.
Okay. I had a question actually when while you were speaking about the materials you have available to do this research. Obviously, diamonds are not cheap material to to assess. Do you have any issues getting enough, just enough material to work on to do this type of research? And is it possible ever to use, after a diamond has been manufactured, use the parts of a diamond that um, contained inclusions,
Yeah.
and keep them intact enough for you to be able to do research?
Yeah, that's an excellent point. So a lot of the information we have is possible because you're able to screen millions of diamonds, and find those very rare examples that have inclusions like this. So you need to have that, flow of faceted diamonds and the ability to study them non-destructively. But beyond that, as you mentioned, the study of offcuts, pieces that have been trimmed off of, especially larger type 2A diamonds or type 2B diamonds, the ability to study inclusion bearing pieces that have been trimmed off of those diamonds during manufacture is tremendously important. And I've learned a lot by being able to take some inclusions like the metallic inclusion I showed you where I've polished and you could see inside. That's something you can't do with the client-owned faceted diamonds coming through the laboratory. You really rely on having at least some samples that you can do destructive analyses on, that you can polish open, that you can analyze their chemistry and do something more robust in terms of a complete analysis. So I'm always looking for inclusion-bearing offcuts of diamonds like these. It's something that can be difficult to track down, but even having a few pieces, especially if we've got known origin information, that's a hugely valuable sample to have. So yeah, I'm always looking for things like that.
A question here from Sumil Shah that I mentioned before. I don't fully understand this question, so I'm going to read it out, Dr. Smith, and I imagine you'll understand it better than me. How would you relate to the energy of super deep diamonds and the diamonds found much closer to the Earth's surface? And he said that by energy he means the measurement of crystals' energy in terms of hertz. Is there a difference in the energy of super deep diamonds compared to others?
Yeah, I'm not sure if I understand that question fully myself, but I would say the diamond in terms of its crystal structure, a diamond is a diamond to some extent. So the crystal structure that we have for lithospheric diamonds is the same as what we see in sublithospheric or super deep diamonds. It's still the same configuration of carbon atoms. They're covalently bonded, the same crystal symmetry and the same bond lengths. So a lot of the properties that would be attributed to the vibration of the crystal structure or anything like that should be the same for these two categories.
Okay, thank you for answering that. We've got 2 minutes left, so if anyone's got any more questions, please post them in the comments. I just wanted to close with one of my own questions, which was whether just looking at the comparison between natural diamonds and lab-grown diamonds, are there any inclusions present in lab-grown diamonds that also tell us something about how a diamond was grown? It's like, is there any sort of parallel in lab-grown diamonds?
Yeah, absolutely. So, lab grown diamonds are often grown with the intention of making something inclusion free, but they do sometimes incorporate some material. For instance, CVD, chemical vapor deposition diamonds, they can have these kind of wispy graphitic marks where you've got carbon that's been incorporated into the crystal as it's growing, and that carbon didn't actually crystallize as diamond. So it's non-diamond carbon. It's almost graphitic. And you don't really see anything beyond that in terms of an inclusion. So it's telling you that this environment where the diamond is growing has a lot of carbon and not a lot of other stuff. That makes sense because this diamond is growing in a partial vacuum. It's surrounded by plasma and you've got carbon atoms and hydrogen in this environment. So you don't have a lot of solid materials to trap. And then the other kind of lab-grown diamond, HPHT grown diamonds, those can sometimes contain metallic inclusions. So little droplets of the metallic iron, nickel, cobalt rich flux, the melt that this diamond has grown in. So sometimes they can contain little droplets of that metal. That is, at a glance, kind of similar to the metallic inclusions that we see in CLIPPIR diamonds, like this one I've shown in the bottom left. Now, in detail, there are big differences between those inclusions and the resulting diamonds, but it's interesting that there is some kind of parallel between nature and laboratory in a bit of a sense like that. But yeah, lab-grown diamonds can have inclusions, and they do speak to the processes by which they form.
Thank you. Just finally, I wanted to ask a question that actually your team sent in in a summary of the topic before this, which I don't think you. I'm not sure if you directly addressed it in your presentation, so I thought I'd ask it myself. Um, are but I think I do know the answer. Are diamonds still being formed today?
As far as we know, the answer is yes. We think that, the Earth is still moving in terms of its plates. It's still got subduction happening. And we've got some diamonds that we've really dated as young as 90 million years and old. Okay, and that sounds old, but in terms of a geologic timescale, 90 million years ago might as well be today. So I think it's pretty likely that there are still diamonds being formed today. The problem is they're forming in the mantle, and there's almost zero chance that we would ever see those diamonds form and then be brought up to Earth's surface in a kimberlite. The time span there is just too great. So, for right now, even if there are diamonds forming at present day, the diamonds we have at Earth's surface are the only diamonds we're ever going to see and be able to touch and appreciate.
Very well. I felt like I should say that the recording of this will be available in 90 million years, given that this is a geology session. But in truth, it will be available in the next few days. I thank you, Dr. Smith, for joining us, and everyone, of course, for submitting questions. I certainly learned a lot about super deep diamonds, but also about other stuff to do with diamonds I wasn't quite expecting to learn about on this session. If anyone has any further questions, please don't hesitate to post them on this LinkedIn post for this event. A reminder that this episode of Gem Talks is brought to you by GIA, the Geological Institute of America, protecting consumers and supporting the global gem and jewelry trade since 1931 through research, education, and laboratory services. Thank you, everyone, and goodbye.